friends, welcome to the channel Physics by IITians. Today we shall understand the importance of experiment in physics in this lecture, and we shall discuss about the revolutionary experiments that change the concepts of physics or ideas of physics. So let's start. Before discussing the video, we have an announcement that we have started online test series which consists of 5 tests, 10 tests and 15 tests. You can choose accordingly, and the cost have been kept minimum for your benefits. So the first test question on 16th August will be very easy and conceptual basis, just to encourage your thinking capability and confidence. So let's start the video. The first experiment, that is very famous experiment, that is Galileo's Tower of Pisa experiment. What Galileo did, we shall understand this. Let us take two balls of lead. The one that is 10 times bigger and heavier than the other. So let them drop together from 30 feet height, and they fall together at the same time on the ground. So this proves that Aristotle is wrong. Earlier Aristotle told that the ball which is 10 times bigger or which is heavier than a lighter ball or lighter object, the heavier object will fall much more faster than the lighter object. But this is totally wrong, and the time of descent was independent, or time of descent is independent of their masses, and that was described by Galileo with this is famous experiment, that is Galileo's Pisa experiment. And the next revolutionary idea that came with the experiment, which was done by Michael Faraday with his discovery of electromagnetic induction in 1831. And he told and he experimented that a curl of electric field can be produced by a time varying magnetic field, or curl of E is minus del B del T. What does it mean? That is, a changing magnetic field can generate electricity. So curl of E is minus del B del T. If you move this magnet, and the magnetic flux will be also changing, and there will be current in this coil, so you will get deflection in the galvanometer reading. Okay, and the next revolutionary idea is the Young double slit experiment, and it was done in 1801. Before Young's double slit experiment, there was a Newton corpuscular theory of light. That is, Newton assumed that light is a stream of particles, and he named the theory as his corpuscular theory of light. But Young double slit experiment, what Young have shown, that when monochromatic light passing through two narrow slits illuminates a distant screen, a characteristic pattern of bright and dark fringes is observed, and this pattern is caused by the superposition of overlapping light waves originating from two slits. That is the phenomena of interference, and it is a direct proof of wave nature of light. Let us discuss it more. Suppose we have a light source, and this is a monochromatic light source. We have two slits, and these two slits can interfere with each other, and there is a skin pattern in the skin, that is light dark this kind of pattern we observe, and we all know this kind of pattern can be observed through the interference phenomena, or can be explained through interference of phenomena of light, where two monochromatic wave interfere with each other with in phase or within opposite phase, and the in phase gives us the bright fringe, and the opposite phase interference gives us the dark fringes. So this can be illustrated only from the wave theory of light. So at that moment, the wave nature of light was demonstrated by Young's, and it was accepted by Young's other fellows. And then another revolutionary experiment in the form of photoelectric effect, and it was done in 1887, and it was described by Einstein in 1905 with his famous photoelectric equations, that is h nu equals to phi naught plus the k max, that is the kinetic energy of the electron. What is the photoelectric effect? The photoelectric effect is the emission of electrons when electromagnetic radiation such as light hits a material. The electrons that emitted in this manner are called photoelectrons, and it's a proof of quantum nature of light, or photon nature of light, and in 1905 Einstein explained it using Planck's quantum hypothesis. So what it is, look here, this is a light and this is a metal surface, and when light of certain frequency is falling on this metal surface, there are generation of electrons, or there are ejection of electrons from the metal surface, and this is not generation. So this ejection of electrons, if you apply a battery, then these electrons can produce the, will be get accelerated, will get, and then the produce and certain electricity. What is happening here? So this, look here, these are metals, and we know, all know that metals have free electron gases, or metal have free electrons. So if this incident photon have sufficient energy to hit these free electrons and eject it from the metal surface, this can produce or generate some currents, and these currents are known as the photoelectric current, or these electrons are known as photoelectrons, and this one can only be explained from the quantum nature of light or photon nature of light. So this is again the establishment of quantum nature of or particle nature of light. So some experiment that examines the wave nature of light, some experiment that examines the particle nature of light. Then again another beautiful experiment, that is division-Germer experiment, that was done from 1923 to 1927 in the Bell lab by the two famous physicists Clinton Division and Lister Germer. What they have shown, that electrons that is scattered by a surface of a crystal of nickel metal displayed a diffraction pattern, and this confirmed the Louis de Broglie hypothesis of wave-particle duality, and it was an experimental milestone in the creation of quantum mechanics. What they have done, suppose this is the electron gun, where the electrons is here hitting this target material, that is the nickel crystal, and this is our detector, which can measure the diffracted electron beams varying this angle phi. Okay, and this is another picture, it shows you, this is, suppose this is the crystal, and there are the lattice spacing between the crystals. So the accelerated electrons here, the target hitting the target, and we are getting here the diffracted electrons, and the pattern with the intensity, if you draw the pattern, that is the accelerating voltage along the x-axis and intensity along the y-axis, we get diffraction pattern of electrons. So this is a direct proof of the wave nature of particle, because electron is a wave and it is showing a diffraction phenomena, which can be only explained from the wave nature. So light have also both the natures matter and particle. So electrons also have both the natures matters and particle, and these are fundamental theories of quantum mechanics, and the Division-Germer experiment was an experimental milestone in the creation of quantum mechanics. So hopefully you understand from today's video. This is another beautiful picture which shows you the diffraction pattern of electrons. So we shall discuss more about the experiments. Don't forget to like, share and subscribe to the channel. Don't forget to join the test series. The cost has been kept minimum for your benefits or for students' benefits. So all the best. Thank you.